Recording. I'm sharing my screen. I am looking for my slides. And they're going to be down here. This I actually kind of like. It just pops up with my last thing I had open. No, I don't want to save my squiggles on the slides. We were on slide 15, and I was drawing something slightly different. I was doing this. Oh no, let's just do this one. Let's not even do that. Because of I don't want to keep the charge stored on a capacitor. That's the eraser tool. I'm going to put a big inverter at the end. So I can build the knot of this anyways. A is going to the gate here, B is going to the gate here, C is going to the gate here.
So since we're doing all these, we just tied all three of those parallel transistors to ground. Do we not need a 5 clock signal?
Oh yeah, we do, you're right. I left a transistor out. These all get tied together. There's a reason why I crashed my computer. And this goes to phi. It's drawn much better in the notes. And then I put another transistor up here that's PMOS. This goes to phi. And I'm going to buffer my output to give me a stronger signal. So I'm just not relying on the capacitance of that node to hold it up. And my buffer's an inverter. So that conveniently did that. Okay. Noise margins out. Okay, so one of the things, we're going to talk about these in more detail. One of the things I lose compared to standard CMOS is my noise margins are going to get lopsided. The output voltage is going to decay with time, and I've got to deal with charge sharing. And if I cascade these, it gets even messier. So the noise margin low is going to be reduced, instead of being VDD over 2, which is pretty ideal, is all the way down at VTN. Really bad. The noise margin high is really good, but I've lost that balance between my noise margins. So if I want good noise margins, I use standard CMOS. Or I use transmission gate. The other cousin of pass transistor. Those have a big smiley face. Pass transistor is it. I lose a threshold. It's not very good, but this one's lousy. Dynamic. I've just completely blown my proportionality between my noise margins out of the water.
So question.
Yes.
If that's the case, then what would be the example of using a dynamic? Like where would you use? So let's say like standard trans we've used more in like analog signals.
Right. Where I see them used is of course inside of memories chips. I have like a memory, and I have you have a 2D array of memory cells, and I have a row drive circuit that I have to fit in whatever the size of the memory cell is, which is really small, because I'm going to have to put another one in the next row next to it. So I got to stack them. So in order to save space and fit this circuit into a smaller area, I might use something like this. It gets used in the row decoders a lot for memory chips. I wouldn't use it in a processor. Just Okay. So we talked about the output voltage decay a little bit, because when this signal goes high and this transistor turns off, if I don't have a path to ground, the charge stored on that capacitor is going to go into leakage currents, and it's going to dissipate with time, and it slowly decays. We're pre-charging Y to VDD. Okay, pre-charge Y to VDD. Then phi goes high. When phi goes high, this transistor goes off. I've got a really good picture of this one here. I have over in the NMOS transistor, I have these diodes.
That's discharging.
Zach. Yes. Okay, unless you're asking a question. I have these diodes here, N plus P plus. So there's like a minus side of the diode and a plus side of the diode right there. I have another diode right here. The diodes are reverse biased, but remember, in reverse bias, they have leakage current, maybe like nanoamps or something like that. But the only place that current can come from is off this capacitor. So it's slowly decaying away through those reverse bias PN junctions. Life's complicated. Oh, good. We get to go talk about buckets of water again. Okay. I got these in 492. I don't know why I just don't. Okay. So if I have two buckets of water that are the same size and I open the valve between them, what we expect to happen is they're going to settle at a final value that is the midpoint of their two levels. Now, if I have a tiny little bucket over here and a big bucket over here, when I turn this valve on, this one's going to go up a little bit. Their final value, they're both going to be equal, but the little bucket is going to take a lot more water to fill the big bucket. If I have a big bucket over here, sorry, and I want to fill the little bucket, it's going to come up closer to the big bucket level, the final value. Same thing happens in capacitors, but in capacitors, instead of having water stored, you have charge stored.
It's like the volume charge, right? So we got like different currents.
Yeah, it's a charge conservation problem. You basically do, and you say, okay, on side A, when the spigot's open, side A, the voltage, the charge equals CV. And then the charge on the other side will be that C times that V. Now, when I close the spigot, the final voltage has to equal the initial voltage. So it's a charge conservation problem. So like right here, now my spigot is a MOSFET, of course. I start out with 0 volt. My Q initial has to equal Q final. Let's just go for broke. Q final. So if I'm looking at example A, my initial voltage, my initial charge is 0 CV times 50 femto, plus the charge on the other capacitor, which is 1.4 times 50 femto. And that is got to equal the final voltage, which when I turn this on, they're going to share a voltage. I don't know what that is yet. I can guess. It's V final times 50 femto plus 50 femto. So looking at this equation, you can pretty much say that there's going to be 7/10 of a volt when I'm done, because the two capacitors are equal. Half the charge off of here, half the voltage, half the charge is going to get dumped over here, and the final voltage is going to be 0.7 of a volt. Now here's the problem. You get this tiny little part, and it's charged up to 1.4 volts. Now this is, the charge here is 1.4 times 5 femto. That added to 0, 1.4 times 5 femto, has got to equal whatever the final voltage is, and the sum of the two capacitors is 55 femto. So now V final is a small fraction, 5 over 55, 1/11 of 1.4. We'll call it 0.14 volts. We'll round to tenths. If I take that same charge right here, but I charge up a bigger capacitor, my final voltage is going to be my initial voltage, 1.4, times the capacitance I had the charge on, divided by the sum of the two. We can see the pattern. So now my final voltage is going to be a lot higher. What happens particularly in memories, you try to charge a 2 femtofarad bus with a 0.2 femtofarad capacitor. And it goes up, but it only goes up like 50 millivolts. So you have to put an analog circuit in there to read that and take it and put it into a real voltage. I just talked about that last class. So yeah, the buckets of water are just like these buckets of charge. A big capacitance is like a big bucket. A small capacitance is like a small bucket. Okay, good. So, charge conservation. We could do this in general for any two capacitors and everything like that. Before the transistor turns on, I have V2 across C2. So the charge on that would be Q equals CV, V2, C2. Plus the charge on the other capacitor, which is V1, C1. That has got to equal the final voltage after I turn it on times the sum of the two capacitors. So it looks like a weighted sum here. A weighted average. We could divide that out and do a little bit of algebra on this equation, and we could solve that one for V final. You're just dividing both sides of the equation by C1 plus C2. Right. Do we want to do these? I'm getting sick of charge sharing. Okay, if the two capacitors are equal, I get V final is half V1 plus half V2. So that would be 0.7 volts. If this one is 10 times bigger, I get now V final is V1. V1 is which one? This one here. 1. V1, which is 0, so I'm going to just ignore it. V2 is 1.4, but it's C2, 5 over the sum of the two is 55. So I get a really small V final. If I reverse these and put the voltage on the larger capacitor, my V final is 1.4 times 55 over, no, 50 over 55. So it's getting pretty close to 1.4 volts. So the relative size of the capacitors matter.
So in this case, when we turn the transistor on and the charge flows over, we're going to have the same voltage across each capacitor.
Yes. Yeah, once you turn that transistor on, you're going to have the same voltage on both capacitors. But whatever charge was on one capacitor, if one's at a higher voltage, will get shared and move over to the other capacitor. Good. I like having people in class. I get questions. What is next? Oh boy, we make it out early. So the same thing happens in these dynamic circuits. Remember, we've got this load capacitor. We want our load capacitor to be big because it's also going to have to, when I turn this off, it's going to be sharing charge across the capacitors we had here. We had capacitance here. It's going to be sharing charge, and when there's load capacitance, there's capacitance all over the place. If some of these transistors, if some of these capacitors are not charged, the charge is going to move off of there, and it's going to cause the output voltage to decay. So you have a limited amount of time that you can leave phi off before you have to go back and do it again, because it will go away. Okay. I could build this in standard CMOS using 4 transistors. Okay, all this is 2 inverters in series. We don't do this. We were probably, yeah, just to prove some stupid point or other. Okay, so phi goes low. Remember, when phi is low, we're in pre-charge. When phi is high, we're in evaluate. So during the pre-charge cycle, my output's going to be high, and it's going to be high on both of these. Now I go into evaluate. What am I trying to say here? I go into evaluate right here. Now I've got A. Let's say A is high. So I don't have to go through this 12 times. If A is high, then I turn this transistor on and evaluate that transistor's on. It's going to pull it low. So it's going to pull this low. It's going to take some time to discharge CL1. And as CL1 discharges, this node will get pulled low eventually. And as it gets pulled low, oh, yeah, okay. I know what I want to say. Now, we've done the, let's just exaggerate this a little bit. Sorry, I'm having one of those moments Jack loved in class. Let's say it takes a long time for this to discharge. I get to the next cycle here. Well, I've already turned this transistor on and I've turned this transistor off. This signal right here, Y1, took a long time to settle. It took long enough to settle that it thought the output was high. It turned that transistor on and drug the signal down anyways. This is bad. You don't want to cascade these circuits because you've got those, that little bit of delay is enough to discharge that node. You have no way to charge it back up. One way you can fix it is to put buffers in there. Now I've taken a circuit that I could have built with 4 transistors and I just made it into a circuit that I have 10 transistors. That's less reliable.
Also, wouldn't that just be 4 inverters?
Yes, it is. It's don't do this.
But if you ever do it, just know to add more inverters.
if you ever screw anything up and it's not working, just add a buffer. Okay. I've got 20 minutes. I might as well start talking about latches and flip-flops. Good. I will probably have time to actually pay service to this. There have been classes where I've spent 5 minutes on latches or 10 minutes on latches and flip-flops, and you get the highly reduced version of this, but let's go through the whole thing. Back when I was at JPL, and with the guy, I told you about the guy who wanted to bury the photodiodes in the substrate, and I ended up working for him. And we developed it into a real system on the chip camera technology. But in order to do that, the first thing we had to do is we'd have to go out to a manufacturer and say, we want to build photodiodes in the substrate. And they would say, that violates our design rules. You can't do that. And then we go find another manufacturer and say, we want to build photodiodes, and we just do this repetitively. We found 2 that would agree to let us build photodiodes in the substrate. Then the next thing is, okay, we want standard cells. We want AND gates and OR gates and all that good stuff and flip-flops. Normally you would go to an IP, somebody who does the IP for that process, and just buy them from them. We could not get anyone agree to sell us our IP once they had done this. This was too weird. So we started out from scratch. We built our own AND gates. We built on our own OR gates. We built our own flip-flops. Building our own flip-flops was a job for Bruce Hancock. And I'll explain that when we get to setup at more time. But the idea behind building a latch isn't that hard. This is a weird way to draw it. The normal way to draw it, most right-thinking people would draw it like this because it makes more sense. There's not all those cross-coupling lines. I take one inverter and I feed it. Okay. There's 2 stable states to this device. It would be stable if I had 0 here and 1 here. Then I'm feeding a 1 back into this one, which makes it a 0, which feeds a 0 back into here, which feeds a 1. It's logic with feedback. Now there's another stable state. I could do this. I could have a 1 here and a 0 here. In that case, my 1 gets inverted, becomes a 0, goes back in here, becomes a 1. And it maintains that state because it likes it, because it's the only 2 stable states there are. There is an unstable state in between there. Let's put an unstable state on here. We put this at 1/2, and we put this at 1/2. It will perfectly balance out and maintain stability. That is the thing you see on your logic diagrams of 310 that looks like the big X's, the unknowns, or the halfway point, and it's bad. We need a way to set the state. So we need a way to actually feed in a value of W or X or Y or Z, any place in here, of a 0 or a 1. Once that value gets fed in there, it will maintain that state forever. So that's the idea of a latch. So now I just have to be able to put input into this thing. Okay. So this is an SR latch. It's the same idea, except I'm doing it with NAND gates. Because an inverter only has 1 input, this has 2 inputs. Each of the NOR gates have 2 inputs. One I call R and one I call S. And what's going to happen here if either R or S is low? If this is low, it's just going to maintain the previous state, because whether this is a 1 or whether the other input is a 1 or a 0, it just maintains that. Okay, as soon as I drive either R or S high, so let's just drive S high. If we drive S high, the OR becomes true, the NOR becomes false. That's 0, That's 0. 0 or 0 is 0, which becomes a 1. Q goes high. That's what I just did. R is low, S is high, it goes high. We could flip those. Let's change this. Might as well just change color too. Okay, we could flip this and look at this case right here. If I drive R1 and S low, what happens? This gate is determined. It's 1 or 1 is 1. This becomes a 0. This becomes a 0. 0 or 0 is 0, which becomes a 1. I have driven it into my Q is low and my not Q is high. I'll prove this to you this time. I didn't do this in 188. If these are 0, if both of these are 0, no, this is skipping. Okay. If both of these are 0, it's just going to maintain the previous state because whatever's on here will just remain on here because it's not going to affect people or gate output. So if both of those are 0, it maintains the previous state. Okay, what happens when R and S are both 1? Something definite happens. This is not an indeterminate state. I know my SR flip-flops were my favorite flip-flop because I hated JKs. Because they're weird. We never used JK flip-flops. Bruce built one once, just to annoy me. If I put both of these signals high, then when this one's high, 1 or anything is 1, which makes this low. And 1 or anything is 1, which makes this low. You come up with a illogical, it's not unstable, it's not undetermined. We know what happens. Q equals not Q equals 0. And Q equals not Q is just, it can wreak havoc on your processor later down the road because you're going to tie Q to things and you're going to tie not Q to things and things, just weird things happen. So it's just generally not used. I just avoided using that state and used my SR flip-flop because I didn't want to deal with the JK toggle thing because I didn't understand it.
So how is it that you avoid that state?
How did I avoid that state? I had my SR flip-flops look like this. They were going, S was going to the output of a counter, and the output of the counter would be, it would decode state 7 of the counter. So it would only go true when state 7 was true.
Oh,
And R would only go true when state 9 was true.
that way they're on separate states and would never be.
And 7 and 9 cannot be true at the same time. And I just had these big master counters running my state machines that basically said, okay, I'm going to set the row timing up by on count 1 of the clock, I open the row, on count 2 of the clock, I do the pre-charge, on count 3 of the clock, I'm going to do this, and I have to hold them up for so many states. It was an amazing thing because the guys before me, they had like this, it was like this pinball machine logic that there was like this pointer that would go through, and it was kind of a quantum thing because the pointer could divide in 2 and come back together again. Sometimes they didn't come back together at the same time. And so there's just like these little enables going through the whole thing and just this jumble of logic. And it would take them months to make any small change to the timing. And when I came in, me and Ken McCarty convinced the boss to just let us redesign the whole thing. And we did this counter thing. And so when Me Too had his weekly meeting and said, I want to change the timing on this, I'd look at him and go, okay, it's going to take me a while. But and the other guys, it would take them months, right? I go in my office, I change the numbers. And then I would go out and take a long hike in the Angeles Crest and go do whatever else I wanted to do and come back the next week and go, it was tough, but we go babysit Bruce. Okay. So yeah, that's how I ensured those things didn't work. Oh, it didn't work. Okay, so we want to look at how a latch works pretty much here. This is, there's no enable on this. So as soon as S goes true, my thing is going to set, and as soon as reset goes true, my thing is going to reset. So we're actually in an unknown state until set happens. So this is my big X. I don't know what happened before I set it the first time. When I set it, Q goes high. I reset it, Q goes low. Pretend this lines up. I set it, it goes high. And it stays high even if I pull set low. And it stays high until I get to this point. And we determine for this particular latch, I get 0, 0. So I've done something really bad in this time frame. I've set and reset true at the same time. What happens is Q goes low. Normally Q bar would equal the naught of Q. But as soon as I did that bad thing, they're both low. And they're going to stay both low until this happens. Reset goes back false. It will go back into a known state. It'll behave once I just not stop doing that. And again, here I'm making that horrible mistake. And so that would stay low. And here this would still stay low until I reset that, and then it goes low high. So you get the idea. It does, SR flip-flops, SR latches do recover from this, but you may have a trickle-down effect, and I've seen this happen in simulations before, where Q and Q bar both go true at the same time, and then suddenly you have this one little thing that gets an X in it, and as you simulate it for longer, your whole screen turns into X's. Don't do that. Okay. Then you got to fix it. Okay. So this is the difference between a D latch and a D flip-flop. This will be enough. This will like blow your mind. Okay. For a D latch, I'm basically enabling it with a signal called phi, which is basically my clock. Phi is always my clock. When the clock is high, D passes through this transistor and gets to here when phi is high. When phi is low, this transistor turns on, and I just feed back the value that was previously stored to reinforce it. So this is enabled with clock or phi. Okay, not so bad. Now we get to the master-slave clock flip-flop. To let Bruce do it. Okay. We've got two signals here, and they're two different clocks. And they have to look like this. So here is phi 1. And I may get this wrong. And this is phi 2. They are something like non-overlapping clocks or something like that. I cannot have them. Let me look at the circuit, I'll tell you. I don't want them on at the same time. That's a non-overlapping clock, and I got the right polarity, I hope. So they cannot be on at the same time. So phi 2 is going to almost look like not phi 1, but it's got to cut off before phi 2 comes on. There's this tiny little gap of time in between there. And then it stays low, and it's got to stay low until after phi 1 comes down. So there's another tiny little gap of time in between there. And these are non-overlapping clocks. I have to make both clocks out of one clock. So there's like little delay tricks and things like that, that's all inside the part of the flip-flop that Bruce does. Okay. So what I want here, when phi 1 is true, this transistor goes on. So phi 1's on, phi. That transistor goes on, and this transistor has to be off. And whatever's on D passes through 2 inverters to here. Phi 2 is still off, and it will get stored here. It's just going to stay there. Okay. Then what happens next? Phi 1. Phi 1 goes off. Reason why I didn't do this. Phi 1 goes off. And all of them are off at once. And then later on, I turn phi 2 on. When phi 2 goes on, this one rolls through here. So I get it stored on here in this short amount of time. I managed to store it. Then I turn phi 2 on, which also turns this transistor on. And when that transistor turns on, then I can pass it to the output. So it's a 2-stage process. One is getting the signal from D and storing it on that middle node. The next part of the process is going from the middle node to the output. So there's a slight delay in there, which makes all things possible. I really should shut up at this point. Do I want to even talk about that? Right, there's my non-overlapping clocks, and this is, and we'll just talk about that one. Okay, we'll talk about that. Basically, what I have done, I have not created a device that, and I'll try to explain this better when we get back next class. I'm fading out here. Is instead of creating something that triggers on the edge, what I've created is something that triggers on a clock pulse that's extremely short. That's the gap between these non-overlapping clocks. So it's like a latch with an enable, but it's only enabled for a very short period of time. That is a little bit before and a little bit after the clock edge. And I'll try to explain that better tomorrow, but I think I'm done. Yeah, this is why. And you can tune these things. Oh, this is what Bruce would do. He'd sit there and he'd tune these overlapping edges of the clocks by making, you'd actually have to delay the other clock and invert it. And you'd make these make these circuits that would act as delay lines for the clock by tuning the size of the transistor and everything, and get them so that you had a setup and hold time, and your setup and hold time was basically equal. You had to, setup time is how long the signal needs to be stable before the clock edge to guarantee that it gets latched in, and hold time is how long it needs to be stable after the clock edge. It's like the width of that enable pulse. And you can tune that with analog delays within your flip-flops. And that was a Bruce Hancock job. It was not a Julie job. It was amazing too. Nobody understood what he was doing. We'd go into our meetings and he'd just show us the simulations and we'd all nod and Just go, okay, can you make the setup time a little bit different? And that would like another 2 weeks off. Or we just go, okay, that looks good. And his flip-flops always work, so we didn't really complain. Okay, I'm gonna let you guys go. If you have any questions, I'll stick around for a little while. Oh, who am I looking for? I'm looking for Danielle. And oh, Danielle's here. Okay, and Sigwy, who will probably be watching on video because it's 3 o'clock in the morning.
I had a question about the last slide.
Okay,
So I was away from the keyboard for like a minute. So what was
Yeah, I
the
know.
focus on? Okay.
that's all it would have taken. What's going on here?
What, not on this slide, but on, I'm sorry, the overlapping clocks. So what was the focus on the non-overlap interval? What is that? What is the
Okay.
significance of that?
If I turn both of these on at the same time, then D goes into here, gets inverted twice, and then immediately goes, it would immediately pass through this one to the output. So D would immediately pass the output if I turn both those clocks on at the same time. We want to delay it a little bit around the clock edge to get things to stabilize.
So that's only when they're both low because they're inverted to both be high.
Well, when they're both high, if they were both high, we don't want them to be both high at the same time. And you can see that in this diagram, they're never high at the same time.
What happens if they are?
Then D just passes right through immediately to Q with no enable and no clock edge.
Okay, and that would be the non-overlap interval.
Yeah. So we got to put that little overlap interval in there so that we can take D and store it here, and then turn this thing on so it's cycling around and it's stored, and then we can turn phi 2 on. Well, that happens at the same time. It's when after this gets turned off, after phi 1 gets turned off, this starts cycling around here. Phi 2 goes on, and then it's fed to the output. It's a little bit of a delay between the input and the output. And the amount of the delay is that non-overlap interval, which is where we have to squeeze all our setup and hold time. And I'll talk about why that's important in the next class, setup and hold time. A lot more detail.
Okay, and about the previous slide before this as well.
Okay. There's a lot of squiggles on that one too.
So what's going on here? This looks kind of similar to slide
Yeah.
44.
It's the same, this is the same circuit that's on slide 44. That's a edge triggered flip-flop. I've got to add that master slave component in there to get the edge triggered, so I have the delay between the clocks. This right here is just an enable without the master slave. As soon as I turn phi on, my output is going to go with like a little bit of a gate delay to Q. So if I change D and phi's on, Q changes. But if I change D here, I need to go through a clock edge between both that high and low transition before Q can change.
So is the purpose of the double inversion just to add a bit of delay to the system?
It's part of the latch. It's part of the storage, because when phi is off, I have that back-to-back inverter in there, and it reinforces. If I have a 0 here, I get a 1 here, I get a 0 here, 0's fed back. So it's adding some feedback in there that reinforces and keeps the signal low or keeps the signal high, even if I don't clock it or don't enable it for a long time.
So we just want to pull the opposite out for
Right.
any. And what about, so on the bottom diagram, we have 2 back-to-back inverters. Are we just not showing that we're pulling out the D negative, or are we not pulling at all?
Where they're pulling it out of is they're pulling the Q bar out of right before the inverter and the Q after the second inverter.
So is there no purpose to the first, to like the master gate?
Oh, the first inverter here?
Yeah.
Yes, there is. It is basically, it's acting as a buffer. You could just put a straight wire between there, but with 2 inverters, you've got a buffer, so it gives you better signal strength on the output.
Okay. I
Yeah.
think I understand this now.
Yeah,
Thank you so much.
Yeah, usually you use, if you want to buffer something in a digital circuit, you use 2 inverters, because that's, yeah, you can't, it's hard to get positive logic.
Okay. Thank
Yeah.
you, Julie.
Okay,
Have a nice day.
you too. Okay. Anybody else?
I just love this analogy. A double inverter is like a double negative on a beeper
Yeah,
because you're just extending the word count.
yes.
But it's not like
The circuit I used the most was 2 inverters back to back.
So you're saying it's like an electronic double swing?
yeah.
Yeah, because, okay, what happens is like the way we designed our gates, and specifically we designed them, every inverter, every AND gate had to be able to drive 10 loads. If I had to drive 12 loads with something, what I would do is I would take that one output and I'd run it through 2 inverters and I'd run it through a second set of 2 inverters and drive half of them off of one and half of them off the other. So just to guarantee that you have a strong signal when you don't have control over where your outputs are going. They could be going to crazy printed circuit board designer who thinks he can drive a motor off of his Arduino. You put a big buffer there so you don't damage your own circuit. And so maybe the motor just spins a little bit. I've seen seniors do that. Yeah. Yeah, it was there was a group of mechanical engineers in a senior capstone. They come to me and they show me, goes, look, there's something wrong with this Arduino. I know my code's right because I can light up an LED, and they stuck the LED in and goes, look, I can light up an LED. Then they pull the LED out and they stick a motor in there, go, but I can't turn the motor. What's wrong with the Arduino? What's we show them how to use a pass transistor at that point. Okay. I will see you guys later. I'm going to stop this so I can stop this.